Welcome to today's Explainer. We are living in a completely wild era right now. We're seeing AI models that can run entirely offline on a smartphone, instantly solve complex math, or directly process audio to understand human emotion. It's honestly pretty magical to experience. But what exactly is happening behind the scenes? Well, today our goal is to demystify deep learning. We're going to break down how artificial intelligence actually works under the hood for someone with absolutely no technical background. And we're going to do this without getting completely lost in the weeds of complex equations. Instead, we'll walk through clear visual steps to show you exactly how a machine learns to think.
Okay, so here's our roadmap. We're going to cover what deep learning actually is, look at its fundamental building blocks, see how stacking those blocks builds complexity, figure out how these networks actually learn, and finally, look at how we keep them on track.
All right, let's jump right into section 1. What is deep learning and where does it fit into the hierarchy of intelligence? Let's start way zoomed out. Artificial intelligence, or AI. At its absolute core, this is just the practice of building algorithms that process information to make decisions. That's the whole umbrella. So whether we're talking about a clunky chess computer from the 1980s or the modern voice assistant on your phone right now, if a machine is processing inputs to make a choice, it's AI.
Now, zoom in one level, and we hit machine learning. The real game changer here is the shift from human instruction to data-driven learning, right? In old-school traditional programming, an engineer literally handwrites every single rule. But with machine learning, the computer looks at a bunch of examples in the data and figures out how to do the task without us explicitly holding its hand for every single step.
And zooming in one more time, we hit our main focus, deep learning. This is a very specialized slice of machine learning that uses deep neural networks. It basically extracts super complex features directly from raw data. So instead of a human having to explain what a corner or an edge looks like, the deep learning model just figures it out entirely on its own through a hierarchical process. Moving to section 2, let's look at the absolute microscopic core of these massive systems, the single neuron. If you take away literally one thing from this entire explainer, make it this. The perceptron, which is our digital neuron, runs on a wonderfully simple 3-step math recipe. Step 1, the dot product. It takes inputs, multiplies them by weights to decide how important they are, and adds them up. Step 2, bias. It just adds a simple number to shift that result up or down. And step 3, the activation function. It passes that final number through a nonlinear function. That is the whole thing. Multiply, add, activate. But wait, let's talk about that third step, the activation function. Why do we even bother with it? Well, because real life is highly nonlinear. It is messy, complex, and dynamic. Imagine trying to draw one perfectly straight line to separate a chaotic jumble of red and green dots on a graph. Often you just can't do it. A straight line is way too rigid. So, to fix that rigidity, we use nonlinear activation functions. This gives our simple little neuron the superpower to draw curved boundaries. For example, we've got sigmoid, which squishes any number into a value between 0 and 1. That's absolutely perfect if you need a percentage probability, like a yes or no answer. Then you have ReLU, which outputs anything from 0 to positive infinity. These functions give the network the flexibility to actually map the complexities of the real world. All right, section 3. We've got our single neuron, but what happens when we start stacking them for complexity? To build a digital brain, we take those single neurons and group them into what we call layers. Every neuron in a layer looks at the exact same inputs, but applies its own unique independent weights. Then we stack those layers on top of each other to build a deep neural network. This is where the real magic of hierarchical learning happens. The first layer might just see basic lines and edges. The next layer combines those edges to find corners. The next turns corners into shapes, until eventually, boom, the network can recognize something as incredibly complex as a human face or a spoken word. It builds abstractions step by step. Okay, on to section 4, how neural networks learn. We have this massive architecture, but how does it actually figure things out? Let's ground this with a real-world example from an introductory class. Say we have a student who attended 4 lectures and studied for 5 hours. We ask the network, will this student pass? Now, a brand new, untrained network is just going to guess randomly. It might spit out, say, a 10% chance of passing. But let's say we know from historical data that this student absolutely did pass. So the network's guess of 10% is totally wrong. When that untrained model messes up, we don't just scrap it. We use something called a loss function. This mathematically measures exactly how far off that 10% guess is from the actual ground truth of 100%. A high loss means the model is doing a terrible job. A low loss means we're getting closer to the truth.
To actually fix that error, the network enters what's called the learning loop. First, it calculates the loss. Second, it uses an algorithm called gradient descent to find the downward slope of the error. Think of it kind of like walking down a hill blindfolded, just feeling around with your feet to find which way is downhill. Third, using a truly brilliant trick called backpropagation, it sends that error backwards through every single layer of the network. And finally, it tweaks all those individual weights just a tiny bit. It does this loop over and over, slowly improving. Now, a super important variable here is the learning rate. This dictates exactly how big of a step the model takes when adjusting its weights. If the step is too small, the model will take literally forever to learn. If the step is too big, it might completely overshoot the optimal answer and ruin everything. Luckily, modern optimization algorithms, like one called Atom, are adaptive. They basically adjust this stride on the fly to find the perfect pace. We also run into a practical problem here. Calculating the error for millions of data points all at once is insanely slow and computationally expensive. But doing it just one point at a time is way too erratic and noisy. The sweet spot? Mini batching. Researchers feed the data into the model in small chunks, say 32 examples at a time. This perfectly balances computational speed with the accuracy of the learning. Which brings us to our final part, Section 5, keeping models on track and avoiding some major pitfalls. The absolute biggest danger in training a model is something called overfitting. This is when the model basically acts like a student who perfectly memorized the practice exam but completely bombs the actual test because they never learned the underlying concepts. It memorizes the noise of the training data instead of the pattern. On the flip side, you have underfitting, where the model is just way too simple to grasp the complexities of the data at all. We want our model right in that Goldilocks zone. To combat overfitting and hit that sweet spot, researchers rely on a suite of techniques called regularization. Regularization actively constrains the model. It literally stops the network from just memorizing the exact data points and forces it to understand the general concepts. That way, it can actually succeed when it eventually faces completely new, weird situations in the real world. One of the coolest regularization tricks is called dropout. During training, the system randomly shuts off or kills a certain percentage of the neurons on every single pass, say 50% of them. Sounds totally counterintuitive, right? But it forces the network to build redundant, resilient pathways to find the answer, rather than becoming overly reliant on just one specific node. It's kind of like forcing a team to work together even if half the staff randomly calls in sick every day. Another vital technique is early stopping. While the model trains, we constantly test it on a completely separate data set that it has never seen before. The exact second we notice that the model is getting better at the training data, but suddenly getting worse at the testing data, we know it's starting to overfit. So we simply hit the brakes and freeze the training right there. And honestly, that is deep learning demystified. When you step back and think about it, it is pretty mind-blowing. By simply taking that straightforward perceptron recipe, multiply, add, activate, and stacking it millions or billions of times, we create systems that can generate stunning artwork, translate languages, and write code. It leaves us with a pretty provocative thought. If this simple digital building block can already replicate so much of human intuition, what complex realities are these networks going to decode next? Thank you for joining me for this explainer, and keep questioning the data around you.